All right, so we are continuing on with electrostatics. So today we're getting into electric fields, and we're going to talk about electric fields from two different perspectives. We're going to talk about it from a single charge. We're going to look at that first, and then we're going to look if we've got more than one charge. More than one charge isn't as complicated as it seems. It's going to be very similar to one charge. You just do a calculation more than once. So as we've been looking at, there are many different similarities between electrostatic forces and gravitational forces. These are very, very similar. One similarity is you are not in contact. So if I've got 2 point charges that have some electric charge, they can exert a force on each other without touching. This is what a field is. And we've talked about fields. We've talked about it with gravity. You've got a gravitational field around the Earth. It influences everything that's on it, whether it's touching or not. Same thing with something with electric charge. They've got electric field. And just like gravitational fields, our electric field will depend on two things: the size of the charge and the distance to the charge. Just like in gravity, it's the mass of the object and your distance between centers. So it's very, very similar. Like I said, this unit is a lot just comparing to gravity and how that looks. Questions on that? So in order for us to have some sort of electric field, an object needs to have charge. So if something has charge, it means you've got extra electrons, or you have less electrons than you should. So that object no longer is neutral. It has either a positive or negative charge. Yeah. Yeah. Anything else that also has some sort of charge will have that. So you've probably seen this in old science lessons a long time ago. If you take like a balloon, you rub it against your hair and you pull it off, your hair is attracted to the balloon. Have you seen something like that? Or if you've done, what's the other one you can do? The what? Yeah, so rubbing the balloon against the wall and it sticks there because you've got a static charge. When you are walking on carpet in your house and then you go to touch a door handle and you get that electric shock, you are gaining a charge by rubbing your feet on the floor, and then when you touch something metal that's grounded, you release that extra electrons, or you gain it from the door handle, depending on if you're positively or negatively charged. So like I said, you're going to see lots of very similar equations. So E, being our electric field, is equal to the force electric divided by the charge. Can anyone tell me what this looks like with gravity? Mm-hmm. Yeah, so this is very similar to your acceleration due to gravity. Here we're talking about electric field strength. In gravity, we're talking about a gravitational field strength. And here, force electric over charge. With gravity, it's force of gravity divided by mass. Does this have what each of these are? Yeah. So these are what each of those means. I will get on to what a charge on a test object is. I will explain that in a sec, because that one might not make sense at this point. Again, you might see this written as electric field or electric field strength. Sometimes you'll see it with that little vector arrow on top of it to indicate it's electric field and not energy. Thankfully, the questions are worded in such a way you should be able to tell the difference between electric field and energy. So substituting in the equation we learned last week, we plug in what force electric is, we end up with this equation. So KQ1 over R squared, and again, this is very similar to our gravitational field, where Q1 is the charge that is causing the electric field. If you remember with gravity, this was mass 1, and that was the mass of the object that was creating the field strength. So now it's the charge that's creating that field strength. Yeah?
Is the radius in comparison of something, or is it like the bigger number?
So the R value here is going to be the distance between the two objects. So similar to gravitational field strength. But your R value, we typically, we don't deal much with the radius between objects. Like if you remember with like the Earth and the Moon. If we wanted to figure out the R value, we'd go radius of the Earth plus the distance between them plus the radius of the Moon. The radii that we deal with in this is so small we just ignore it.
And we don't compare with the second object, it's like Q1 and Q2.
Yes, for the field strength, it's just the charge that's creating the field. Yep. Okay, so with these kind of fields, they're vectors. So electric field's a vector, just like gravitational acceleration is also a vector. And we can draw these as arrows. We didn't so much do this with gravitation, simply because it's always towards whatever object. But here we need to look at what does it look like between different objects, because now we've got something a little bit different in that we have pushing and pulling. So let's take a look. So with a attraction or a repulsion, so if we've got this is a, oh, come on. If this is going to be, oh, I think I know what the problem is. I'm in the wrong program. So let's think about this while this is loading. So if I've got a positive charge, the field lines are going to be drawn depending on what a positive charge would do. So if I had, say here I had a positive charge, and I put another positive charge here, what direction is it going to go? If I stick this one here and this can't move, what happens to this object? It wants to repel. So no matter where I put it, if I put it on this side, it'll repel. Put it down here, it's going to repel. So if we have a positive charge, and I want to look at the direction that those arrows would point, it's going to be as if I were putting a positive charge there. That would be the direction that the line would point. Get back to this. So if this is a positive charge, if I put another positive charge here, it's going to be repelled. So the field line is going to point away. Same thing here, repelled, repelled, repelled. Anywhere in between here is also going to be repelled. So this is what the field lines are going to look like around a positive charge. So if you're ever confused as to what direction these are going to point, imagine if you have some positive charge and think where would they move. So it doesn't matter where it is. If it's here, it's going to go away. You put it down here, it'll push away. So these lines are always going to push away from positive charges.
So we assume there's another charge that's positive next to it?
Yeah, so that's when I said before something about the test charge. You imagine a positive test charge is there. What would happen to it? Because the reason we needed to do that, let's see if I can think of an example I can explain. Well, let's just go back to gravity. So if I am talking about, say, this is the Earth, and I put someone here. Don't draw this because we're not doing that. What direction is my field line going to point where this person is? It's going to point towards the center, right? And then same thing over here, I'm going to have something that points towards the center. Same thing here, something that points towards the center. And that is just because if you have mass, they're going to be attracted. And it doesn't depend on who this person is. My gravitational field strength is just dependent on where they are. So that's the same thing with this. My electric field strength shouldn't depend on what this second charge is. It just depends on what's this distance between them and what is the size of this charge. So my test charge here is not an actual charge because I don't want what the charge of this is.
Will that direction ever change?
That's what we'll look at here with the negative charges. So this is what happens if we've got positive charge. If I've got negative, what directions are the arrows going to go? They're going to what? Mm-hmm. Yeah. So my test charge is always positive. So if I looked at what would a positive charge do here, it's going to be attracted. They want to stick together. So it's going to look the exact same as what I had for the positive charge, except my arrows are reversed. They're not pointing away, they're pointing towards. So this is what your field lines would point like. Again, my electric field strength just depends on two things. What is this charge, and how far away is my other charge? I don't care what the other charge is, I just want to know what's the distance. Yeah? Yes. But nothing's moving because we just want to know what's the field strength. Again, same with gravity. When we talked about what's the acceleration due to gravity on the moon from the Earth, it's not that the moon is actually moving towards the Earth. We just want to know what's the acceleration at that point.
Like if I'm looking at the first one, the test charge isn't moving like that for that positive.
Nothing's going to be moving. Not in this case. That's because we're dealing with electrostatics. So static meaning it's not moving. So yeah. So if I was dealing with at this point here, there might be a charge, there might not. If I wanted to calculate what is the field strength at this point, take into account this, the distance, and then I can figure out the field strength. Whether it's attractive or repulsive will depend on this is positive or negative, and you'll need to indicate that in your answer. But it doesn't actually matter what is at this point. I just need to know what is the field strength. You'll see that once we get into some questions here. Any other questions with this? So you'll notice with this, in comparing to gravity like we've been doing, this would be like a gravitational model. These would be the field lines of your gravitational field strength around the Earth or around any mass. The reason we now have this is because we can have repulsive forces. And that just depends on what the charges are. Yeah, so with field lines, it's just saying the closer the arrows are together, the more strong the force is, or the field strength. So closer to the surface of whatever object you're dealing with, you have a greater amount of field strength. This is for next section of notes. Okay, here's the examples. Let's give this a try. So what is our electric field strength at a point where this Coulomb charge, so this should, again, this is a micro, so 10 to the power of negative 6, charge will experience a force of this. So we want gravitational field strength. We've got now the charge of our test point. We don't have the charge of whatever the object is. So this one, we're just going to use the very first equation I gave you. So electric field is the force divided by the charge. And again, the charge here is whatever our test point is. In reading this question, can you see why this is the test charge and not the charge that is causing the field strength? Mm-hmm.
This is an application of X on the negative, I think,
No, it's not because of the negative there. Yeah, so it's saying that this charge is going to experience this force. Meaning this is not the object that is going to create the field strength. This is the object that is going to experience that field strength. So this is a very subtle difference between the two, and you'll see with the other question, I think, if I remember correctly, what the difference is. Mm-hmm. Mm-hmm. Yeah, you can have any combination of the two. Yep. So we have the force, we have the charge. Notice here with the charge, I did not put negative. So you're not going to put the negative in there. You're just going to put the positive of it. But in so in the equation, we're not putting that negative there. With our electric field strength, we're just going to have this. I don't know why there's this drawing over there, since that's not the charge that's making the field. Ignore the little drawing, don't put that. Just put the rest up here. Need to change that. So like I said, the confusing part about this unit is going to be when to put negatives and when not to. So it's a great thing that you can make your own formula sheet, and you'll be able to add that in. You'll see a better summary of it all once we get to the end of this unit. So we do not put the negatives in the equation. So in this case, this is our field strength, and the direction of the field strength is going to be dependent on what the charge is that is causing this gravitational field strength. So depending on if it's positive or negative, if it's negative like it's shown here, this is going to be towards the charge.
Do we write that? Do we write towards
No, because in this question, I don't give it to you. Just like with gravity, you didn't need to write the acceleration due to gravity is towards the Earth's surface or towards the center of the Earth. It's kind of just given. Any questions with this? Okay. So let's try this. So now we're told at a distance of 0.75 from a small charged object, we've got this field strength. We want to know what is the distance from this same object that'll produce a new electric field strength. So what's going to help for this is, let's first figure out what is that actual charge. So just so you can see what's happening here, we're told at this point here, at this distance away from a charge, we have this much field strength. And then I want to find the new R value to get this new electric field. So here's what we're told. This is a little bit confusing. We're told at this distance, here is our electric field strength. What is this now new point that gives us a different electric field strength? So the thing we want to first solve is, what is the charge? This is kind of like one of those questions of if you triple the mass, double the radius kind of thing. It's similar to that, except I can actually solve for what the charge is. So we have our electric field strength equation. We have electric field, we've got E1, we've got K, 9 times 10 to the power of 9. We want what is this charge? and we know the distance between them. So we can solve for Q, and we get a number. And then it's simply a matter of taking that exact same equation and then solving for R2. So we do this for E2, solve for the radius, we get 0.53 meters. Questions with this? Yeah? Mm-hmm. Give you a sec to jot this down. Yeah.
If you were told what the charge of that other object is,
Mm-hmm.
if it was they were being repelled from each other, what
So you're saying in the last question, if your electric field is repelling, would they both be negative? This is the problem with that question. Oh no, well it tells you it's negative. The one charge is negative. So if it was repelled, the other one would have to be negative. So yeah. If you didn't know if that was negative, repulsion can occur if they're both positive or both negative.
would the field strength itself be negative? Like to indicate that they're being repelled?
No. The field strength is typically given as a positive number, whether or not it is attracted or repelled. Yeah, and then we just indicate direction with the arrows. All right, so we're good with this? I think that is the end of the set of notes. Okay, so what do we got? We got 9:53. We end at 10:45. So I'll give you a little bit of a break here till 10 o'clock, and then I want to cover the next section here.